Hey there, it's Shannon MATHCHICK Myers, and today we'll be looking at section 7.4. Sorry, I think it did an automatic numbering deal for me. And 7.4, you're going to see these concepts as you go into later on in Calculus 2 and into Calculus 3. And so it's important for you to really start getting a handle on these concepts of arc length and it's actually area of surfaces of revolution. So here we go. Arc length of a smooth curve. Arc length is approximated by summing infinitely many, and I'm going to write in line segments, period. A rectifiable curve is one which has a finite arc length, a sufficient condition for the graph of a function f to be rectifiable between a comma f at a and b comma f at b is that f be continuous on the closed interval from a to b. And sorry, that is f prime is continuous. A function of this type is considered to be continuously differentiable on the closed interval from a to b, and its graph on the interval, closed interval, a to b, is called a smooth curve. So we've seen a lot of theorems and definitions where a function had to be continuous on a closed interval and differentiable on an open interval. For this one, it needs to be differentiable on the closed interval because we'll be including the endpoints we'll be integrating. All right? So here we go. We've got this arc. This arc is, I don't know, we can give it some scale by adding in a coordinate axis or writing in a coordinate axis. This would be our x, this would be our y. And let's suppose this is A, and A is equal to some x0. And so you'll have an ordered pair, right? So if you go up and meet this graph here, this ordered pair would be at some x0, y0. And then let's go ahead and call this one here B. B happens to be xn because we're going into subintervals for the definition here and the concept. And if you just keep looking at different points you can make, so this one here would be the point xn, yn. And what we do with this is we make infinitely many little line segments on the arc and then we add them all up. So say this is x1, y1, and you'd have to kind of imagine that this is magnified, and you would just keep going. Call this one xn minus 1, and these would just keep going. Your ordered pairs would keep going all the way until you got to the end of your arc, or the portion of your arc that's of interest. And so what we have here is we connect, you know, all of these infinitely many distances and on this smooth curve, and then the better your approximation is, the more close to the actual arc length you'll get. Okay, so let's check it out. We've got A is equal to x0, and x0 has to be less than x1, which is less than x2, less than, keep on going, to x sub n minus 1 is less than x sub n, which is equal to B, our right endpoint. Now, the change in delta xi, if you kind of scooch in on these, I made sort of a thick line. You remember we had an ordered pair here. You know, I'm going to make this less thick. This is too thick for my evil plan. So you had all of these little tiny areas, which basically made up our arc length. Right? And then, so here, if you were to look at, say, this little triangle that is made, the vertical length would be the change in y in your second subinterval, because we're looking at this little subinterval here. And then this here would be your change in x2. But what are these? This would just be, the first one would be y2 minus y1, and the second one is x2 minus x1. All right, so you come back in here, and in general, your change in xi is going to be delta xi minus delta x sub I minus 1. Your change in the ith y interval would be, or your change in y in the ith interval would be delta yi minus delta yi minus 1, sub I minus 1. Cool? And then we simply use the distance formula to derive this. And so arc length is denoted by an S. Arc length is going to be your smooth curve from A to B inclusive. And we can start out by thinking of it as the summation, as I goes from 1 to n, of the square root of x sub I minus x sub I minus 1, that quantity squared, plus y sub I, and then minus y sub I minus 1, that quantity squared. And then S will equal to the summation as I goes from 1 to n of the square root of, well, we said that this was delta xi. That will be squared, plus delta yi squared. Now we'll do a little bit of trickery. I'm going to extend this square root, and I'm going to multiply just the second term in the radicand by delta xi squared over delta xi squared. What that will do, I'm going to move over here, sorry, is allow us to rewrite this as the square root of, I'm factoring out a delta xi squared. What remains is 1 plus quantity delta yi over delta xi squared. So you've got delta yi squared over delta xi squared is all of this. And then we are factoring out a delta xi squared. So that's going to be, I have a product, right? And so when I square root delta xi squared, I'm going to get a delta xi. Now I know that this can be a plus or minus, and so since this formula was derived this way, you may need to adjust the sign to keep the arc length positive. So we will get 1 plus delta yi over delta xi squared, and then we have evaluated that square root of delta xi squared to get delta xi. Because we're going to form an integral for this, we want this to be on the right side. So here we go. Oh, and sorry, these have our summations. All right, so now as the width of each subinterval, called the norm of delta, approaches 0, the number of subintervals n will approach infinity, okay? And so because of this, we can say that S is equal to the limit as the norm of delta approaches 0 of the summation from I equals 1 to n of the square root of 1 plus delta yi over delta xi squared times delta xi, which is a factor to that square root. Cool, cool, cool. And I'm going to just add in the length S of the graph. Now make sure you don't use an uppercase X, because that is going to denote surface area later on. All right, so now here we go. Since f prime at x exists for all x that belong to the interval from open interval from x sub I minus 1 to x sub I, because remember x sub I is bigger, the mean value theorem ensures that there's going to exist, so that backwards capital E means there exists some Ci. Ci is an element of xi minus 1 to xi such that f at xi minus f at x sub I minus 1 over xi minus x sub I minus 1 is equal to f prime at ci. Should look a little bit familiar maybe. Cool, cool. Now, delta yi over delta xi is going to equal to f prime at ci, since f prime is continuous on the closed interval from a to b, the square root of 1 plus f prime at x squared is also continuous. Thus, we can take this limit as the norm of delta approaches 0 of the summation from I equals 1 to n of the square root of 1 plus f prime at ci squared times delta xi, and rewrite that as a definite integral. So you'll have the definite integral from a to b of the square root of 1 plus f prime at x, the quantity squared, dx. And there you have arc length. So official definition of arc length, let the function y equals f of x represent a smooth curve on the closed interval from a to b. The arc length of f between a and b is equal to what we just derived. S equals the integral a to b of the square root of 1 plus f prime at x squared with respect to x. Now, if you have a smooth curve, x equals g of y, on the closed interval from c to d, the arc length of g between c and d will be s equals the integral from c to d of the square root of 1 plus g prime at y squared with respect to y. Cool, cool? All right, excellent. So let's take a look at an example and see how this works. All right, so we want to find the arc length from -3 to 4. This is an ordered pair going clockwise to 4, 3. Along the circle, x squared plus y squared is 25. So it's easier for me to match a grid to my circle. So let me put that over here. And the circle is centered at the origin. For some reason, it's easier to move the circle than the line. Okay. So that should be pretty good. This would be our x-axis, y-axis, and then we've got, do you see we have a circle with radius 5, because 5 squared is 25. And then the arc length of interest is going to be up in the quadrants 1 and 2. So y will be positive, and it won't trace itself more than once. So here, four, three, two, one, 1, 2, 3, 4. 2, 3, 4, 2, 3, 4. So we'll have -3, 4. It will be about here. And then we're going clockwise until we get to 4, 3. Sorry. So this is 4, 3. So our arc length is moving this way, right? And it goes all the way here. This is the arc length of interest. Groovy? So here we go. Let's do the easy part first, right? We want to work out our magic on the integral, using our calculus to find the arc length, but circumference is also arc length, right? So remember, the circumference of a circle is C equals, you can either do pi times the diameter. Since we have the radius, I'm going to say 2 times pi times r. So in our case, r equals 5, right? So our circumference will be C is equal to 2 times pi times 5, which is 10 pi. Now we need to find 1/4 of the circumference, would just be 1/4 of 10 pi, which would be 5 pi over 2. Looking at a calculator, 5 times pi divided by 2 is approximately, we'll call it 7.8540. And that would be just in units, because arc length is in that, is not area, it's a linear measure. Okay, good. Making sure I wrote it down right. Okay, so that's what we want to match. So now let's use the calculus way. So in general, arc length, we can do this one as a function of x or a function of y. You're probably more used to working with a function of x. So our arc length, I'm just going to do it as the interval from a to b of the square root of 1 plus f prime at x squared dx, right? So we need to find a few things. So if we look at y squared, isolating that, we would get 25 minus x squared. We're in the positive part for the y values, so I'm just going to choose the positive square root of 25 minus x squared. So y prime, or we'll just say y prime, which is the same as f prime, is going to be negative 2x, using the chain rule, over the square root of 25 minus x squared, and then we have a times 2 there because it's 1/2 times what's inside to the negative 1/2. That's how it dropped to the bottom. Dividing out those 2's, y prime will be equal to negative x over the square root of 25 minus x squared. Cool, cool? Now, that needs to be squared, doesn't it? So if I square both sides of this, y prime squared is going to be x squared over 25 minus x squared. And so let's plug that into our integral. So s is equal to, what is our a? Beautiful, negative 3, and our b is 4, and these are the x values, a to b. So it's not that first ordered pair, it's looking at x is traveling. The domain values are going from negative 3 to 4. So we will have, I'm just going to write the square root as the 1/2 power. We'll have 1 plus f prime of x squared was x squared over 25 minus x squared. That'll be raised to the 1/2 power, and it's with respect to x. There's a lot of algebra in these, so make sure, you don't get lost in the algebra. But, you do need to show your work. This is a calculus class that is for, future engineers, doctors, mathematicians, computer science people. So you just, need to learn these things. And it's not that we don't have the technology to solve them. It's that it trains your brain, kind of like your brain is training for a marathon. It trains your brain to think analytically. So we're going from negative 3 to 4, and then we have, when I get a common denominator, I will have 25 minus x squared, and then plus x squared all over 25 minus x squared. All of that is to the 1/2 power, and it's going to be integrated with respect to x. Simplifying, s equals the integral from negative 3 to 4, and then we'll have the x squareds zero out. We're going to have, I'm going to separate these because you can separate the quotient of square roots so that we recognize this. We have 5 squared minus x squared in the denominator under a square root. Root 25 is just 5, so s will be 5 times the integral from negative 3 to 4 of 1 over the square root of, I'll give you a hint, the formula is like a squared u squared. Anybody have any ideas? Awesome. You're going to get arcsine, right? So s is equal to 5 times arcsine, or inverse sine, of u over a. Our u is just x, so we'll have x over 5. And that's evaluated from x is equal to negative 3 to x is equal to 4. So S will equal to 5 times arc sine at 4/5 minus arc sine at -3/5. And let's go ahead and get an approximation for this so that we can compare it to what we got for 1/4 of the circumference, all right? So here we go. 5 times second inverse sine, 4 divided by 5, or you could just put in, you could also just put in 0.8. And then we need to insert in some parentheses because you're multiplying the 5 to that whole difference. And then we have minus inverse sine. There it was a -3/5. You could have also written it, taken out that minus and written it as a plus using the negative angle identity. And enter, and look what we got. Woohoo! Approximately 7.8540. Cool, cool? All right. And so we verified that this matched 1/4 of the circumference of a circle. Groovy, huh? So it's kind of cool because if we were to sort of kind of look at this and look at this, you could kind of see that that's a quarter circle. Cool, cool? All right. So next up, the area of a surface of revolution. I'm not going to go into the whole kind of proof of this because I usually try to do the proofs of things where I think that you'll remember it better if you see it. I think that you'll remember the formula for the surface of revolution, area of surface of revolution, because that will, it's not too different than the arc length. All right, so just relate it to your arc length formula. So a surface of revolution happens when the graph of a continuous function is revolved about a line, some kind of axis. The resulting surface is a surface of revolution. So if you think about, I don't know, if you think about the difference between the kind of like a sleeve, if you will. So if you covered a cup with some sort of sleeve, that would give you like your surface area sort of thing. It's not exactly that, but kind of an image. So before, when we were doing this technique, we were revolving a whole region around our axis of revolution. But for this one, what we're doing is we're just revolving this arc around. And so what it does is it kind of just gives you this shell, right? It doesn't give you the solid inside. It gives you the surface area, right? So like the difference between the surface area of a lake versus the volume of the lake. Groovy? Now, you will be dealing with a radius. So the radius will, at any given time, is going to be, this measure here. How far is your axis of revolution to the arc that's being rotated? So this is a picture of when you have a horizontal axis of revolution, as you can see right here. Okay? All right, so definition. Let the function y equals f at x have a continuous derivative on the closed interval from a to b. The area, capital S, of the surface of revolution formed by revolving the graph of f about a horizontal or a vertical axis, all right? So it can be horizontal or vertical, but if it's a function of x, you're going to use this formula. S is equal to, you get 2 pi because you've done a full revolution making a circle, okay? So remember, this is multiplied by 2 pi from that rotation, that revolution all the way around, and then the integral from a to b of r at x. So oftentimes that ends up just being x or just being y, so don't make it harder than it is, all right? And times the square root, this is from your arc length formula, right? Times the square root of 1 plus f prime at x squared, and then with respect to x. Groovy? Okay, so r at x is the distance between the graph of f and the axis of revolution. If x is equal to g of y on the interval from c to d, all right? So if you have some function of y, x equals some function of y, then the surface area is capital S equals 2 pi integral c to d of g r of y, my bad, times the square root of 1 plus g prime of y squared with respect to y, where r of y is the distance between the graph of g and the axis of revolution. All right, so here we go. How it works. Finding the area of a surface of revolution. So on this one, my apologies, I didn't put the bounds. So we're rotating about the y-axis. We're given a function of x, and x goes from 0 to 3. So drawing our graph, when x is 0, we get an output of 9, right? So we're revolving about the y-axis, right? And then we have our graph. So we said we would have a point at 0, 9. We would have a point if you plug in, and then 3, 0. And if you plug in 1, we're going to get 8. If you plug in 2, we get 5. And so our arc looks like this somewhat. Okay? Now that arc is going to be rotated about the y-axis. So if you watched our other video on volume, the disc and washer method, you saw that you end up making kind of, this, to kind of see what it looks like, the shape looks like, you end up making sort of this ghost graph over here. And then you've got this circle here. And so it's kind of like the outside of a thimble, right? Outside of a thimble. So you'd have this surface area. So it's not the inside of it, it's the outside of it. Cool? Okay, so remember the arc length is the original drawn in the pen on the right side. So our radius is this length here at any time. So this is our radius in terms of x. So at any time, how far away is your arc from your axis? Well, when it's 1 unit away, right? When it's when you're at x is 1, how far away are you from your axis? You're 1 unit away, right? So right here, if you looked up here, when x is 1, you're 1 unit away. When x is 2, how far are we away? We're 2 units away from our axis. So at any given time, right, you're x units away from your axis of revolution. Now, oftentimes, these integrals are easier. That's the good news. So s is equal to 2 pi times the integral x equals 0, that's our a, x equals 3 is our b. And then we're going to have r of x, which is x, times the square root of 1 plus, it's written as y, so I'm going to just write this as y prime squared. But what is y prime? Y prime is just negative 2x. So we're going to get 2 pi times the integral from 0 to 3 of x times 1 plus negative 2x, the quantity squared, and then that whole deal is raised to the 1/2 dx. So s equals 2 pi integral 0 to 3 x times 1 plus 4x squared, all of that to the 1/2 with respect to x. So if we take a look here, if u was equal to 1 plus 4x squared, du would be what? 8x dx, right? So we need to balance out the integral by 8, which means we have to divide by 8. Cool so far? So now this means we can directly evaluate this integral. We'll have pi over 4 when we simplify, and then we'll have the quantity 1 plus 4x squared raised to the 3/2 divided by 3/2 evaluated from x is equal to 0 to x is equal to 3. And when we invert and multiply, we will have 2/3 times pi over 4, which would be pi over 6. And so then we would have 1 plus 4 times 3 squared. That whole thing is to the 3/2 minus 1 plus 4 times 0 squared, that whole thing to the 3/2. So S will be pi over 6. 3 squared is 9. 9 times 4 is 36. So it's awkward, but we'll end up getting 37 to the 3/2 minus 1 to the 3/2, right? Which is just 1. And that's in units. Cool, cool. And actually that's in units squared, or square units, because it's an area. Cool, cool. So that is exact. Most of the time in my class I'll ask for an exact answer unless it's specified otherwise. And guess what? We're all done for this lecture. So I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, hey, hit that subscribe button, like the video, maybe share the video, and enjoy the rest of the Calculus 2 playlist. Bye.